Right now, without you feeling a single thing, the entire solar system is moving. The Sun, Earth, every planet, every moon drifting at over 40,000 miles per hour through a cloud of invisible gas between the stars. And we are approaching the edge of that cloud. What waits on the other side is not empty space. It is something denser, something our best instruments have only partly mapped, something that, the last time the solar system crossed a cloud like it, may have shrunk our entire protective bubble to inside Earth's own orbit. If you enjoy space content that actually changes how you see your place in the universe, subscribe. You won't want to miss where this goes. From the invisible cloud we're living in right now, to the ancient moment Earth may have sat completely unprotected under open space, to the 2025 discovery that has scientists questioning how fast we're actually moving through the universe. Get ready. We begin. You have never felt the solar system move, and yet it does. Every second of every day, the sun pulls every planet with it on a journey through the galaxy. Right now, you are traveling at over 40,000 miles per hour. The chair you are sitting on, the ground beneath it, the entire planet, all of it is sweeping through space at a speed that would get you from New York to Los Angeles in about 4 minutes. Most people know Earth orbits the Sunday. Fewer people know the sun itself is also moving, and almost no one thinks about where exactly the sun is heading. The sun is not floating in clean, empty space. The gap between stars is filled with something. Thin clouds of gas and dust drift between solar systems, spread across distances so enormous that your brain will resist the scale. The sun moves through these clouds the way a ship moves through fog. You cannot see the fog from inside it. You just keep moving forward. Right now, the solar system sits inside one of those clouds. Scientists call it the local interstellar cloud, though many researchers just call it the local fluff. That name sounds harmless. And for the most part, this particular cloud is thin, incredibly thin. A cubic inch of it holds fewer particles than the best vacuum chambers humans have ever built on Earth. And yet it is still there, still pressing, still shaping the edge of our solar system in ways that took decades to understand. Here is what makes this moment different. The solar system is approaching the edge of that cloud. Scientists have been watching the signals building for years. The sun may cross into a new region of space within the next 10,000 years. That sounds like a long time. On human scales, it is. On the scale of the galaxy, that is tomorrow morning. And the region ahead has never been fully mapped. Astronomers know it exists. They can measure some of its properties from a distance. But the exact shape of the boundary, the density of what lies beyond it, the strength of its magnetic field, those are still open questions. The tools humans have sent into that direction are few. The data they return is limited. Scientists are working from partial sketches, not a complete picture. Now here is the part that should get your attention. This has happened before. The solar system has crossed through interstellar clouds in its long history. And at least once, the consequences were severe enough to leave evidence in the rocks of Earth and the surface of the Moon. When astronomers started connecting those ancient clues to modern measurements of the heliosphere, the story got bigger than most people realized. The heliosphere is the sun's protective bubble. It wraps around every planet in the solar system. It acts as a shield, and its size, its strength, its reach into space, all of that depends on what the sun is moving through. The cloud ahead could change that bubble, compress it, weaken it, or do something stranger. Scientists are still working out exactly what the region beyond our current cloud is made of, and the answer to that question matters more than most people know, because the last time the answer was denser than expected, something remarkable happened to Earth. Picture a soap bubble floating through a bathroom. Inside the bubble, the air is calm. The pressure holds it together. Outside, the room is full of different air, different moisture, different temperature. The bubble's shape depends on the balance between inside and outside. The solar system works the same way. The sun blows a constant stream of charged particles outward in all directions. That stream pushes against whatever gas and dust fill the surrounding space. Where the pushing balances, a boundary forms. Everything inside that boundary is the sun's domain. Everything outside belongs to the galaxy. That boundary is called the heliosphere. And right now, the heliosphere sits inside the local fluff. The local fluff is a region of interstellar gas and dust, about 30 light-years across. 1 light-year is roughly 6 trillion miles. So the cloud is about 180 trillion miles wide. The sun entered it somewhere between 45,000 and 150,000 years ago, though scientists still debate the exact timing. Inside this cloud, the gas is warmer than the surrounding space. The temperature runs around 17,000 degrees Fahrenheit. That sounds extreme. A candle flame is around 2,000 degrees. But in space, temperature and heat work differently. The gas in the local fluff is so thin that there are only about 5 particles per cubic inch. Compare that to the air in this room, which holds roughly 440 quintillion particles in every cubic inch. The cloud is essentially a ghost. You could pass your hand through a column of it and never feel a thing, and yet it still matters. Even a ghost exerts pressure. Even that thin stream of particles presses against the outside of the heliosphere constantly. It shapes the bubble. It defines one wall of the boundary that keeps most of the galaxy's radiation from reaching the inner planets. Scientists learned to measure the local fluff by watching how it absorbs starlight. When a star sits behind a cloud, its light passes through the gas on the way to Earth. Certain wavelengths get absorbed in patterns that act like fingerprints. Different elements leave different marks. By reading those marks, astronomers can figure out what the cloud is made of, how fast it is moving, and roughly where its edges are. The local fluff is moving relative to the sun at about 52,000 miles per hour. From the sun's perspective, this cloud is flowing past like a slow river. From the galaxy's perspective, both the sun and the cloud are orbiting the center of the Milky Way at hundreds of thousands of miles per hour. The scale of these motions keeps layering on top of each other. What makes this cloud unusual is where it sits. The solar system exists inside a larger hollow region called the local bubble, a cavity about 1,000 light-years wide blown out by ancient supernova explosions. The local fluff drifts inside that bubble. The sun drifts inside the local fluff. Layer inside layer. But the local fluff does not go on forever. It has an edge, and something sits just beyond that edge. Scientists call the neighboring structure the G-cloud. The sun is moving toward it, and the properties of the G-cloud are different enough from the local fluff that crossing into it could change the heliosphere in ways scientists are still calculating. The edge of the local fluff is not a sharp line, and that makes the situation harder to read. For most of history, nobody knew the solar system was inside a cloud at all. Space between stars looked empty from Earth. Telescopes showed stars and galaxies, but the thin gas drifting between them was nearly invisible. It took decades of measuring starlight, building sensitive instruments, and piecing together hundreds of small signals before astronomers could say with confidence, "We are inside something." And once they confirmed that, the next question came fast. How big is it? And how close are we to the edge? The answer surprised a lot of people. Scientists now believe the edge of the local fluff is somewhere within a few light-years of the sun in the direction the solar system is currently moving. A few light-years, in galactic terms, is almost nothing. The nearest star to our sun, Alpha Centauri, sits about 4 light-years away. The cloud's edge in the direction we are heading may be closer than that. NASA's astronomy picture of the day put it plainly in a summary of this research. The sun may leave the local fluff entirely within the next 10,000 years. Some models say even sooner. But here is where the story gets complicated. Scientists are not certain the sun is still inside the cloud at all. Some measurements suggest the solar system may already be in the transition zone between the local fluff and the neighboring G-cloud. The two clouds press against each other, and where they meet, the conditions are mixed. The density changes, the magnetic field changes. The temperature shifts. It is less a clean border and more a slow collision between two invisible weather systems. Mapping this boundary is genuinely hard. Researchers cannot fly a spacecraft to the edge of the cloud and take a photo. Instead, they build their picture from dozens of indirect signals. They measure how the interstellar gas moves relative to Earth. They watch how neutral particles from outside the solar system stream inward. They track changes in the magnetic field at the heliosphere's outer edge. Every one of those measurements comes with uncertainty. Stack enough uncertainties and the boundary gets blurry. What scientists do agree on is the direction. The solar system is moving roughly toward a region in the constellation Hercules. That is the direction the Sun has been heading for millions of years. And the local fluff's edge, in models built from the best available data, appears to lie somewhere in that general path ahead. So the solar system is not randomly wandering. It is heading toward a specific region, a region that connects to the G-cloud, a region where the interstellar conditions are different from what the heliosphere currently experiences. The transition may already be starting. Voyager spacecraft data and signals from a mission called the Interstellar Boundary Explorer have both returned readings that suggest the outer heliosphere is more complex and more responsive to outside conditions than older models predicted. Something out there is pressing differently than it used to. Scientists keep refining the models. Each new dataset narrows the uncertainty a little, but the core question remains open. The edge is close. The transition is real. And what lies on the other side of that transition is the subject of serious scientific debate. What scientists found when they looked closely at the boundary region stopped more than a few researchers in their tracks. Just beyond the local fluff, another cloud waits. Scientists call it the G-cloud. It sits in the same general part of the galaxy, close enough to the local fluff that the two structures interact along their shared edge. The Sun is moving in the G-cloud's direction. Depending on the model, the heliosphere is either already brushing its outer layer or will reach it within a few thousand years. The G-cloud is denser than the local fluff. Denser means more particles per cubic inch pressing against the outside of the heliosphere. More pressure means a smaller bubble. A smaller bubble means less shielding for the planets inside. Scientists measured the G-cloud the same way they measured the local fluff, by reading what it does to starlight passing through it. Different stars sit at different distances from Earth. When astronomers compare how the light from nearby stars is absorbed versus stars farther away, they can identify layers in the interstellar gas. The G-cloud shows up as a distinct region with its own temperature, its own density, and its own magnetic field direction. And that magnetic field is the part that kept researchers busy for years. The magnetic field outside the heliosphere does not just sit there quietly. It presses against the Sun's bubble. It bends it. The heliosphere is already shaped like a comet rather than a perfect sphere, with a long tail streaming away from the direction the solar system is heading. The outside magnetic field is one reason for that shape. The G-cloud's field points in a different direction than the local fluff's field. When the heliosphere crosses from one magnetic environment into the other, the geometry of the whole bubble changes. The pressure angles shift. The tail reshapes. Regions of the heliosphere that currently face the incoming flow will face a different flow after the crossing. Researchers published models trying to predict what this crossing will look like. The results vary depending on how dense the G-cloud turns out to be at the exact location the Sun enters it. If the density is low, the change may be modest. The heliosphere shrinks a bit. The shielding weakens slightly. Cosmic rays coming in from the galaxy increase slightly. Life on Earth probably would not notice. If the density is higher, the change gets more significant. The heliosphere can compress inward substantially. The outer planets spend more time exposed to galactic radiation. The radiation environment of the entire solar system shifts. And if the density is much higher, the kind of density found in a particularly thick patch of interstellar cloud, then something far more dramatic could happen. Something that may have happened before in Earth's history. Something that left physical marks. But that part of the story belongs to a different chapter. For now, the G-cloud itself raises a more immediate question. Nobody has measured its exact density at the point the Sun will enter it. The models use averages. The real density could be higher or lower than the averages suggest. That uncertainty is not a small thing. The difference between a mild crossing and a dramatic one could be the difference between a slightly different radiation environment and a heliosphere compressed to a fraction of its current size. Scientists are still gathering data, and the next clue came from the farthest spacecraft humanity has ever launched. The Sun is not just a ball of fire sitting still at the center of the solar system. Every second, it fires a continuous stream of particles outward in every direction. Electrons, protons, helium atoms, all of them moving at hundreds of miles per second, blasting away from the Sun's surface and spreading through space. Scientists call this the solar wind. The solar wind does not stop at Pluto. It keeps going. It pushes out past the farthest known planets, past the small icy bodies at the solar system's edge, billions of miles from the Sunday. And as it pushes outward, it carves out a region of space where the Sun's influence dominates. That entire region is the heliosphere. Think of it like a force field. The solar wind creates pressure. That pressure pushes back against the interstellar gas coming in from outside. Somewhere out there, the solar wind slows down and eventually stops. That stopping point is the outer wall of the heliosphere, a boundary called the heliopause. Everything inside the heliopause is in the Sun's bubble. Everything outside belongs to the galaxy. The heliopause sits roughly 11 billion miles from the Sun in the direction the solar system is heading. That is about 120 times farther from the Sun than Earth is. At the speed of light, it takes about 16 hours to get there. At the speed of a commercial jet, you would need over 1.5 million years. But here is what most people do not visualize when they hear solar system. The heliosphere is bigger than anything most people picture. Every planet, every moon, every asteroid, every comet in the known solar system fits inside it with room to spare. The heliosphere is the true outer boundary of the Sun's territory, and that boundary is not a rigid wall. It breathes. When the Sun goes through an active period and increases its output, the solar wind gets stronger and the heliosphere expands slightly. When the Sun calms down, the heliosphere contracts slightly. The whole bubble pulses over time, responding to the Sun's own activity cycle. But the solar wind is only half of the equation. The other half is what pushes back from outside. The interstellar gas, the local fluff pressing against the heliosphere, is what defines the outer edge. If that gas gets denser, it pushes back harder. The heliopause moves inward. The bubble shrinks. Less of space is inside the Sun's protective domain. This is the fundamental physics behind the entire story of what the solar system is moving toward. The heliosphere is not permanent. Its size is a negotiation between the Sun's output and the outside pressure. Scientists have sent only 2 human-made objects past the heliopause, Voyager 1 and Voyager 2, launched in the late 1970s. Both crossed the heliopause decades after launch, and both returned data that changed how scientists understood the boundary in ways nobody had fully predicted. One of those surprises involved the solar wind stopping completely. The solar wind starts at the Sun's surface and never really stops, it just loses the fight. Charged particles leave the Sun at speeds between 200 and 500 miles per second during calm periods. During solar storms, that can jump to over 1,000 miles per second. These particles spray in every direction simultaneously, a constant invisible storm pouring away from the Sun in a sphere. As that wind expands outward, it thins out. The same number of particles spreading across an ever larger sphere means the density drops the farther out you go. By the time the solar wind reaches Earth, it is 1,000,000 times less dense than the air at sea level. By the time it reaches the outer solar system, it has thinned dramatically further. And yet even that thin wind is enough to push back against interstellar space. The process works like this. The solar wind travels outward at high speed. At some point, it collides with the incoming flow of interstellar gas. That collision creates a zone of compressed, turbulent material. Scientists call this zone the heliosheath. Inside the heliosheath, the solar wind slows down sharply and becomes chaotic. The particles pile up, the magnetic field folds over itself, and the whole region becomes messy and complex. The inner edge of this turbulent zone is called the termination shock. That is where the solar wind first hits resistance and drops from supersonic speed to something much slower. Voyager 1 crossed the termination shock at about 94 times Earth's distance from the Sunday. Voyager 2 crossed it at about 84 times Earth's distance, which was different enough from Voyager 1 that scientists knew the heliosphere is not symmetric. It is thicker in some directions than others. The outer edge of the heliosheath is the heliopause, the true outer boundary of the solar system's bubble. But the bubble does not protect every planet equally. The inner planets, Mercury, Venus, Earth, Mars, sit deep inside the heliosphere, far from its outer walls. The solar wind wraps around them, sometimes producing aurora and other effects. But the particles arriving at Earth's location are already well contained within the Sun's domain. The outer planets sit in regions where the solar wind has thinned dramatically. Neptune, for example, sits about 30 times farther from the Sun than Earth does. Out there, the solar wind is still present, but just barely maintaining dominance against the interstellar environment. The planets themselves also have their own magnetic fields that interact with the solar wind. Earth's magnetic field deflects the wind, creating a teardrop-shaped bubble called the magnetosphere around the planet. Jupiter has a magnetosphere so large that, if it were visible from Earth, it would appear wider than the full moon in the night sky. So the heliosphere contains the magnetospheres. The magnetospheres protect the planets. It is shielding layered inside shielding. Remove or shrink the outer layer, and the inner layers face a harder environment. This is precisely why the direction the solar system is drifting matters so much. If the heliosphere changes, every layer inside it changes too. And Voyager's data showed the outer layer was already stranger than anyone expected. The heliosphere holds its shape through constant competition. The solar wind pushes out. The interstellar gas pushes in. The point where those two forces balance is the boundary. Change either side of that balance, and the boundary moves. This is straightforward physics. What makes it complicated is the scale, the time scales, and the wild difference in what a little more pressure can actually mean. Start with a mild case. Suppose the solar system drifts into interstellar gas that is slightly denser than the local fluff. The outside pressure increases. The heliopause moves inward a few billion miles. The heliosheath gets thinner. The termination shock shifts closer to the Sunday. The bubble compresses. In this mild case, the inner planets are unaffected in any direct way. Earth sits so deep inside the heliosphere that even a modest compression leaves it well protected. Cosmic rays from outside the solar system, high-energy particles traveling from distant supernovae, and other violent events would see a slightly easier path into the heliosphere, but most would still be deflected or absorbed before reaching Earth. Life on Earth would likely notice nothing. Now push the scenario further. Suppose the solar system enters a region significantly denser than the local fluff. The outside pressure spikes. The heliosphere compresses more aggressively. The termination shock, which currently sits out near Pluto and beyond, retreats inward. In a sufficiently dense cloud, the heliopause could compress to somewhere near the outer planets. In this moderate case, the radiation environment of the solar system would shift. More cosmic rays would penetrate into the inner solar system. The atmosphere at the top of Earth's atmosphere would absorb a higher flux of high-energy particles. Over thousands of years, this could affect the upper atmosphere's chemistry. Scientists have proposed that this kind of change could influence cloud formation at high altitudes, which in turn could affect global temperatures. The connection between cosmic rays, cloud formation, and climate is an active area of research. Scientists debate the size of the effect, but the direction more cosmic rays in, more atmospheric ionization, more potential for climate influence follows from the physics. Now push the scenario to the extreme end. A cloud dense enough to compress the heliosphere to inside Earth's orbit. In that case, Earth itself would sit outside the Sun's protective bubble. The planet would face the interstellar medium directly. The cold, dense gas between stars would wash over Earth with no solar wind barrier to stop it. Scientists once considered this scenario theoretical, a worst-case model used to illustrate the physics. Then a team ran the numbers on something the geological record had been hiding for years. The answer they got changed the conversation completely. In 2012, something strange happened to Voyager 1. The spacecraft had been traveling for 35 years. Launched in 1977, it had passed Jupiter, then Saturn, then kept going. For decades after leaving the last planet behind, it traveled through the heliosheath, that messy outer zone where the solar wind slows down and the interstellar gas begins to press back. Scientists had been tracking it, watching for the moment it would cross the heliopause and enter true interstellar space. But in 2012, before the heliopause crossing was confirmed, Voyager 1 entered something nobody had mapped on the charts, a region that did not fit neatly into the existing models. The solar wind in that zone had dropped to nearly zero. The outward flow of particles from the Sun, which had been declining for years as Voyager moved further away, essentially stopped moving outward. Instead, the solar wind particles in that zone were flowing sideways along the surface of the heliosphere rather than away from it. At the same time, the magnetic field did not make the jump to interstellar orientation that scientists expected when crossing the heliopause. The field strength increased, but the direction stayed closer to what the Sun's field looked like, mixed up with something from outside. Scientists gave this region a name: the magnetic highway. Particles from inside the solar system were leaking out along it, and particles from outside were flooding in. Then in August of 2012, the transition completed. Galactic cosmic rays, high-energy particles from outside the solar system spiked sharply. Solar particles dropped to nearly nothing. Voyager 1 had crossed into interstellar space, but the crossing had not looked the way anyone predicted. The heliopause was not a clean wall. It was a layered, complex transition zone with regions that mixed solar and interstellar material in ways the models had not captured. The magnetic highway was real and measurable, and it showed that the outer boundary of the solar system was permeable. Particles moved across it in both directions through specific channels. This mattered enormously, because if the boundary was already more complex and more open than the models predicted, then the interaction between the heliosphere and whatever interstellar environment the solar system enters next would also be more complex than the models predicted. Voyager 1 was at that point about 11 billion miles from the Sunday. If you laid 11 billion miles of road end to end, you could drive it at 60 miles per hour for over 21 million years. And what it found at that extraordinary distance was a boundary stranger than any model had prepared scientists to expect. The data Voyager sent back forced a rewrite of the standard picture, and then another mission pointed its instruments at the boundary from a completely different angle and found something even harder to explain. April of 2010, Voyager 1 was about 10.5 billion miles from the Sunday. Scientists at NASA announced something unexpected. The outward speed of the solar wind at Voyager 1's location had dropped to zero. The stream of particles that had been blowing steadily outward from the Sun for more than 3 decades had stopped moving in the outward direction entirely. This was the first direct measurement confirming that a specific layer of the heliosphere existed as scientists had theorized. The layer where the solar wind lost its battle against the pressure, pushing in from interstellar space, and went completely still. Scientists called this zone the stagnation region. Inside the stagnation region, the solar wind did not reverse. It did not blow back toward the Sunday. It simply had no net outward motion. The particles were trapped, compressed, and deflected sideways along the boundary of the heliosphere. Picture a river hitting a dam. The water stops moving forward. It backs up, It flows sideways. It piles up against the barrier. The solar wind was doing something similar, pressing against the outer wall of the heliosphere, losing its forward momentum and pooling in this dead zone before eventually leaking through the boundary. At the same time, Voyager 1 detected the silent solar wind. Its instruments picked up something else. The magnetic field in that region had increased in strength significantly. The field lines were piling up, compressed against the heliosphere's outer wall the same way water piles up against a dam. Scientists had predicted a stagnation region would exist, but the measurements showed it was thicker and more complex than the simple models had suggested. The region spanned roughly 1 billion miles. In that zone, the solar wind was essentially neutralized, crushed against the boundary by the weight of interstellar space pressing back. And this was in the local fluff, the relatively thin, relatively gentle cloud the solar system currently moves through. The question scientists immediately started asking was obvious. If this is what the stagnation region looks like inside the local fluff, what would it look like if the solar system moved into a denser cloud? If the outside pressure increased significantly, the stagnation region would move inward. The compressed magnetic field zone would shift closer to the sunday. The whole structure would reorganize under greater strain. That calculation had real consequences. The stagnation region is part of the heliosphere's defense system against galactic cosmic rays. High-energy particles from outside the solar system have to fight through this zone to get deeper inside. A thicker, more compressed stagnation region under higher outside pressure would change how well it does that job. And Voyager 1 was about to deliver another measurement that made this question even more urgent, because in the stagnation region, one particular type of particle was doing something alarming. At the same time, Voyager 1 detected the dead zone. Its instruments measured something that grabbed scientists' attention immediately. High-energy electrons from outside the solar system, galactic electrons, originating in distant supernovae and other violent events across the Milky Way, had increased in intensity by about 100 times compared to levels inside the heliosphere. 100 times, in a short span, at the outer edge of the solar system. This was the clearest sign yet that the heliosphere does a serious job of keeping galactic particles out. Inside the bubble, galactic electrons are rare. Step across the outer boundary toward interstellar space, and you are suddenly surrounded by 100 times more of them. The heliosphere was deflecting, absorbing, and slowing the vast majority of these particles before they could reach the inner solar system. Now think about what that means if the heliosphere shrinks. These electrons are on the lower end of the energy scale for galactic cosmic rays. The more dangerous high-energy particles, protons and heavier atomic nuclei moving close to the speed of light are the ones that pose the biggest biological risk. But the electron measurement made the principle crystal clear. The heliosphere is not just a boundary marker, it is an active shield, and it works much better than some earlier estimates suggested. The electrons Voyager 1 measured were entering through the magnetic highway and through the stagnation region's leaky outer wall. They were not reaching Earth in significant numbers. The deeper layers of the heliosphere, the solar wind pressure closer to the Sun, the Earth's own magnetosphere, all of those layers blocked most of what got through the outer wall. But the outer wall is the first line of defense, and it responded to outside pressure in real time. Scientists began modeling what a compressed heliosphere would look like for Earth. If the outer wall moved inward, the electrons and higher energy particles currently blocked at the heliopause would gain access to a larger fraction of the solar system. The middle layers of the heliosphere would face a heavier bombardment. Over time, more particles would reach the inner planets. The effect on Earth's atmosphere would depend on how much the flux increased and for how long. Some researchers looked at the atmosphere's chemistry under higher cosmic ray bombardment and found possible effects on ozone chemistry at high altitudes. Others looked at cloud formation data from periods in Earth's history when the cosmic ray environment may have shifted. The data were suggestive. The cause and effect chain was plausible but not proven, and then scientists found a way to check. Earth's geological record contains a chemical fingerprint of periods when the heliosphere may have been compromised. The evidence had been sitting in rock and sediment samples for years. Nobody had connected it to the heliosphere story, until a team finally looked at it from the right angle. But before that discovery, another mission was already finding something completely different at the heliosphere's edge, something that even the Voyager data had not prepared scientists to expect. In 2009, a small spacecraft opened its eyes for the first time and saw something that made no sense. The Interstellar Boundary Explorer, a satellite about the size of a washing machine, spinning in orbit around Earth, was designed to map the heliosphere's outer boundary from the inside. It did this by detecting energetic neutral atoms, particles that travel in straight lines from the edge of the solar system all the way to Earth without being deflected by magnetic fields. Scientists expected to build a mostly smooth map. The heliosphere was shaped like a comet, they knew. The leading edge was blunt and compressed. The trailing edge stretched out in a long tail. The map of energetic neutral atoms coming in from the heliosphere's edge should look roughly like a smeared oval, brighter on the nose side, where the solar wind presses hardest against the interstellar flow. What the spacecraft returned instead stopped scientists mid-sentence. Wrapped across the sky, cutting through the expected smooth map, was a bright ribbon. A long, curved band of energetic neutral atoms, narrow and intense, running from one side of the heliosphere map to the other, 2 to 3 times brighter than the surrounding region, sitting at a distance of roughly 100 to 125 times Earth's distance from the Sunday. No model had predicted it. No existing theory of the heliosphere explained it. The ribbon was just there, sharp and unmistakable, cutting across the expected pattern like a scar. Scientists published the discovery and immediately started arguing about what it meant. One leading explanation came from the way outside magnetic fields interact with the heliosphere. In this model, the ribbon marks a region where the interstellar magnetic field outside the heliosphere runs perpendicular to the line of sight from that region to the Sunday. Where the field geometry lines up this way, the neutral atoms follow a specific path and concentrate. The ribbon would then be essentially a map of the outside magnetic field's direction, painted onto the sky by the behavior of particles at the heliosphere's edge. If this explanation is correct, and it remains a leading idea but not a certainty, the ribbon tells scientists something profound. The magnetic field of the interstellar medium just outside the heliosphere is actively shaping the boundary in a detailed, structured way. The heliosphere is not just being squeezed by pressure, it is being sculpted by magnetic geometry. That means, as the solar system moves into a new region of space, with a different magnetic field direction, the ribbon would move, the heliosphere would reshape itself, the direction of maximum compression would change. The entire geometry of the sun's protective bubble would shift based on the magnetic environment the solar system enters. The ribbon was still unexplained in all its details when scientists tried to match it to their models of the G-cloud's magnetic field. And the G-cloud points in a different direction than the local fluff. If the ribbon reflects the outside field, entering the G-cloud would literally repaint the sky at the heliosphere's edge. The bubble would reorganize itself around a new magnetic geometry. Something that big, reorganizing itself around the solar system, had happened before, and the last time it did, the evidence ended up buried deep in the ocean floor. The ribbon was not just a curiosity, it was a new instrument. Once scientists accepted that the ribbon exists, they realized it carried encoded information about the space just outside the heliosphere. Space that Voyager 1 was only sampling in a single narrow line. The ribbon painted a wide arc across the sky, and wherever it appeared, it was reading out properties of the boundary region in each direction. Think of it like a weather vane. A single weather vane tells you the wind direction at one point. A ribbon of weather vanes stretched across 1,000 miles of sky tells you the shape of the entire wind system. The ribbon told scientists that the interstellar magnetic field just outside the heliosphere had a specific orientation. It was not random, it was structured, and the structure followed a pattern that matched the direction of the larger interstellar magnetic field threading through the local bubble, the enormous hollow region the solar system moves through. This connected the microscopic story of the heliosphere's edge to the macroscopic story of the galaxy's structure. The same magnetic field lines that organize the gas in the local bubble also shaped the specific ribbon pattern that Ibex saw from Earth orbit. For the solar system's journey into the G-cloud, this connection mattered enormously. The G-cloud has its own internal magnetic field, and it points in a direction somewhat different from the local fluff's field. If the ribbon forms where the outside field runs perpendicular to the direction from the observation point to the Sun, then a field pointing in a new direction would produce a ribbon in a new location. Scientists ran models of what the ribbon would look like if the solar system were already inside the G-cloud instead of the local fluff. The ribbon would shift, its arc across the sky would tilt, the bright band would appear in a different part of the heliosphere map. This means, in principle, scientists can track the solar system's progress through the interstellar environment by watching how the ribbon moves over time. Each decade of Ibex observations adds another data point. If the ribbon shows a slow rotation or shift over years, it would suggest the heliosphere is already responding to a changing magnetic environment outside. So far, the ribbon appears stable. That is consistent with still being inside the local fluff, or being in a transition zone where the change is gradual rather than sharp. But stable does not mean permanent. Underneath the ribbon, another finding from Ibex added a second layer to the story. The mission also found that neutral hydrogen atoms streaming into the solar system from interstellar space were coming from a slightly different direction than expected. The stream was deflected about 4 degrees from the direction scientists predicted based on the local fluff's motion. 4 degrees sounds small. On galactic scales, a 4-degree deflection in the neutral hydrogen flow suggests the material just outside the heliosphere is doing something the models had not captured. A magnetic field twist, an uneven density patch, something at the boundary creating a subtle but measurable bend in the incoming flow. Every small discrepancy, like this, added to the growing picture. The heliosphere's outer boundary was not a passive wall. It was an active, magnetically structured interface that responded to and recorded the properties of whatever the solar system was moving through, and what it had moved through before, in Earth's past, left a far more dramatic record than any satellite reading. The heliosphere is not round. Most diagrams show it as a perfect sphere. Textbooks used to draw it that way. Even science museum displays often show the solar system tucked inside a clean bubble. But that picture is wrong, and scientists have known it for a long time. The heliosphere is stretched. One side is blunt and compressed. The other side trails behind in a long tail that extends far into space in the direction the solar system has come from. The whole structure looks less like a bubble and more like a comet or a teardrop moving through interstellar gas. The reason comes back to the fundamental physics of motion. The solar system moves through the interstellar medium at roughly 52,000 miles per hour relative to the surrounding gas. The heliosphere rams into that gas on one side, the leading edge, called the nose. On the nose, the interstellar gas piles up and pushes hard against the solar wind. The heliopause on the nose side is compressed. It sits closer to the sun than on the other sides. On the opposite side, the tail, called the heliotail, the interstellar gas is flowing away from the solar system. The solar wind meets much less resistance there. It streams outward much farther before being stopped. The tail of the heliosphere may extend hundreds of billions of miles behind the solar system, far longer than the nose region. This asymmetry has real consequences for how the heliosphere shields the planets. The nose side takes the direct hit from incoming interstellar gas. That is where the boundary is most compressed and most active. It is where the magnetic field piling effect is strongest. It is where particles crossing the heliopause face the most turbulence. The flanks, the sides of the heliosphere, are somewhere in between. The solar wind there meets side-flowing interstellar gas, and the boundary sits at an intermediate distance from the sunday. Now, add a magnetic field to this picture. The interstellar magnetic field outside the heliosphere is not aligned with the solar system's direction of motion. It comes in at an angle. This tips and distorts the teardrop shape further. The tail does not trail perfectly behind the nose. It skews in the direction the magnetic field pushes it. Ibex observations confirm this skewing. The tail of the heliosphere, mapped by tracking neutral atoms streaming back from that direction, showed a twisted, clover-like structure rather than a single, clean trail. 4 lobes of material, 2 at higher latitudes and 2 at lower latitudes, creating a pattern that looked nothing like the simple tail in the old textbooks. As the solar system moves into a new magnetic environment, the whole shape will change. The nose will reorient. The tail will twist differently. The flanks will experience new angles of pressure. The entire asymmetric structure will reorganize itself around the new magnetic geometry it encounters. This reorganization is not dangerous by itself, but it changes the directions from which cosmic rays can most easily enter the heliosphere. And cosmic rays reaching Earth are one of the physical threads that ties this entire story to life on the surface. The reorganization has happened before. The evidence for it is not theoretical. Nobody has ever flown through the local fluff and taken a photograph. The cloud is invisible. It is too thin to appear in normal light. A camera pointed at the sky sees right through it as if it were not there. The gas is the same color as nothing. The dust, where present at all, scatters light so weakly that it produces no visible haze at these densities. So how do scientists know the local fluff exists? How do they know its size, its temperature, its direction of motion, its density? How do they draw a map of something they cannot see? They use light as a probe. When starlight travels from a distant star to Earth, it passes through whatever gas sits between that star and us. The gas absorbs specific wavelengths of light. Each element absorbs its own specific set of wavelengths, like a fingerprint. Hydrogen absorbs at specific points. Calcium absorbs at others. Sodium leaves its own marks. When astronomers take the light from a nearby star and spread it out into a spectrum, they look for those fingerprints in the absorption pattern. If the fingerprint of calcium appears at a specific shifted wavelength, it means calcium gas is sitting between that star and Earth, and the shift tells scientists how fast that gas is moving relative to Earth. By doing this for hundreds of stars at different distances and in different directions, astronomers build up a 3-dimensional picture of the gas in the solar neighborhood. Stars showing a particular absorption fingerprint at the same velocity tell scientists that a single cloud sits in front of all of them. Stars beyond the cloud show the fingerprint. Stars inside or behind the cloud's edge in different directions do not. This is how the local fluff was mapped. Dozens of stellar spectra, years of measurement, cross-referencing absorption velocities in hundreds of lines of sight. The result is a rough 3-dimensional map of the cloud's shape. The local fluff is not spherical, it is irregular, like most gas clouds in space. It has a thicker core, thinner edges, and irregular lobes poking out in different directions. But the map has limits. The absorption method only works along lines of sight to stars. Between those lines of sight, scientists have to interpolate, guess, based on physical models, what fills the gaps. The cloud could have dense patches or thin holes in regions that no bright nearby star happens to sit behind. This is why astronomers describe the local fluff's edge with uncertainty ranges rather than precise distances. The boundary could be a light year closer than the best estimate or a light year farther. In some directions, the edge is better constrained than others, depending on which stars happen to sit at the right distances. For the solar system's journey, this uncertainty matters. The solar system is heading in a specific direction. How close the edge is in that specific direction is one of the least well-measured parts of the map, and there is another layer of complexity. The G-cloud beyond the local fluff is even less mapped than the local fluff itself. Scientists are trying to characterize a cloud the solar system has not entered yet, using light from stars that happen to sit behind it. The picture scientists have built is remarkable, given the tools available, and it is genuinely incomplete. The next step in filling the gaps came from an unexpected direction: ancient geological samples. Hundreds of feet below the ocean floor, a wall would be easier to understand. If the edge of the local fluff were a clean, sharp boundary gas on one side, no gas on the other, scientists could calculate exactly when the solar system would cross it. They could predict what changes would happen on a precise timeline. The transition from inside the cloud to outside it would be a single moment, like stepping through a doorway. Space does not work that way. The edge of the local fluff is a gradient. On one side, the gas reaches its full local fluff density. On the other side, the gas of the G-cloud, or the surrounding local bubble, thins the material differently. In between, the properties of both clouds mix. Temperature shifts, density shifts, magnetic field orientation changes gradually rather than all at once. This mixing zone is not a thin line. It stretches across light years in some places. The two clouds are not two separate bodies of water meeting in a tank. They are more like two weather systems pressing against each other in the atmosphere. Where a cold front meets warm air, there is a messy zone of storms, mixing, and instability. The boundary between the local fluff and the G-cloud is an interstellar weather front. Scientists call this region the interface. Observations suggest the Sun may already be somewhere inside this interface. Some measurements of the neutral hydrogen flow streaming into the solar system show properties that fit the local fluff model. Other measurements hint at material with slightly different characteristics. The two signals are mixed. That mixing is a signature of being in the transition zone. For the heliosphere, a gradual transition has different consequences than a sudden one. If the solar system smoothly moves from one cloud to another over thousands of years, the heliosphere has time to slowly adjust. It compresses gradually. The geometry of the boundary reorganizes over long timescales. The radiation environment changes slowly. But interstellar clouds do not always have smooth interfaces. Sometimes, a denser knot of material sits at the boundary, a clump where the gas is 3 or 4 times denser than the surrounding material. The solar system could hit a clump like that and experience a rapid compression before the heliosphere adjusts. Scientists cannot predict whether the path ahead contains any such clumps. The maps do not have fine enough resolution to show them. A clump, a few trillion miles across, large enough to matter, could be sitting in the solar system's path and be completely invisible to current observations. This is one of the genuine unknowns that makes the story more than theoretical. The gradual average transition is one scenario. The random clump encounter is another. And the geological record of Earth suggests the planet has faced at least one encounter severe enough to leave a chemical signature across multiple continents. Finding that signature was one of the stranger scientific detective stories of recent decades. It started with someone asking a question about iron, a radioactive form of iron that should not be on Earth in any quantity, and finding it absolutely everywhere. 2 to 3 million years ago, something strange happened to the heliosphere. Scientists reconstructed the event from a computer model built in 2024, published in one of the most respected journals in astronomy. The model started with a simple question. The solar system passes through different regions of the galaxy over its long journey. Some of those regions contain denser gas clouds. What would happen to the heliosphere if the solar system passed through a cold, dense interstellar cloud? The researchers ran the numbers carefully. They modeled the heliosphere's response to different cloud densities. And when they used the properties of a particularly cold, dense type of interstellar cloud, the kind that exists in the galaxy and that the solar system could plausibly have encountered in its orbital path around the Milky Way, the result was extreme. The heliosphere shrank to roughly 22% of Earth's orbital distance from the Sunday. To put that in terms you can picture, Earth orbits the Sun at a distance of about 93 million miles. 22% of that is roughly 20 million miles. The entire heliopause, the outer wall of the Sun's protective bubble, would have compressed from its current position, 11 billion miles out, all the way down to less than the distance from the Sun to Mercury. Every planet in the solar system would have been outside the heliosphere. Mars, Jupiter, Saturn, Uranus, Neptune, all exposed directly to interstellar space. Earth itself would have been sitting outside the protective bubble, bathed in the cold, dense interstellar medium. The solar wind would still exist near the Sunday, but it would have been crushed back almost to the Sun's doorstep. The layered protection system that currently wraps around Earth would have been stripped away. The planet would have sat in open interstellar gas for as long as the solar system remained inside that dense cloud. How long? The model suggested thousands of years, possibly tens of thousands. During that period, the interstellar gas would have pressed directly against Earth's upper atmosphere. Cosmic rays from outside the galaxy would have flooded in without the heliosphere to reduce them first. The radiation environment at Earth's surface would have been meaningfully different from what life experiences today. Scientists were careful not to overclaim. The model was exactly that, a model. It required assumptions about the cloud's density, temperature, and size. Real encounters could have been more severe or less severe depending on the actual properties of whatever cloud the solar system passed through. But the model was physically sound. The numbers worked. A dense enough interstellar cloud can do this to the heliosphere. That part is not disputed. The question was whether there was any physical evidence this had actually happened. Any trace in the geological or cosmic record of a period when Earth sat exposed to open interstellar space. There was, and it had been buried under the ocean floor for 2 million years, waiting for someone to look for it in the right way. The ocean floor is a slow archive. Sediment falls through the water for millions of years and builds up in thin layers at the bottom. Each layer represents a specific period of time. Scientists can drill down into that sediment, pull out a core of material hundreds of feet long, and read the chemical record of the past the same way you might read tree rings. Deeper down equals further back in time. In the 1990s, scientists examining deep-sea sediment cores found something unusual. A radioactive form of iron called iron-60 was showing up in layers that dated to roughly 2 to 3 million years ago. Iron-60 decays with a half-life of about 2.5 million years. That means iron-60 made more than about 20 million years ago would be entirely gone by now, decayed into nothing. Any iron-60 found in rock layers from 2 to 3 million years ago had to have arrived on Earth at that time. Iron-60 is produced in supernova explosions and in certain stellar processes. It does not form naturally on Earth. Finding it in deep-sea sediment layers meant it had arrived from space. Scientists initially connected this to a nearby supernova explosion around that time frame, and that connection is still considered valid. But the researchers working on the heliosphere model looked at the iron-60 data from a different angle. They pointed out that interstellar material, including iron-60, produced in supernovae, would flow freely into the inner solar system during any period when the heliosphere was compressed inside Earth's orbit. When the heliosphere is large, it blocks most interstellar particles from reaching Earth. Neutral atoms can still drift through on their own, but the charged particles and heavier material carried on interstellar flows get deflected. A compressed heliosphere with Earth sitting outside it would allow that material to reach Earth's surface unimpeded. The iron-60 in the sediment layers matched the time frame of the modeled cloud encounter. The signal appeared in layers from multiple ocean drilling sites around the world, meaning the deposition was global. Then scientists found another chemical fingerprint, plutonium-244. Plutonium-244 has a half-life of about 80 million years. Any of it found in geological layers must have come from outside Earth, because natural Earth processes do not produce it in detectable amounts at this stage of the planet's history. A team found traces of plutonium-244 in the same deep sediment layers where the iron-60 signal appeared. Plutonium-244 is produced in supernova events and in rapid neutron capture processes around dying stars. Its presence in Earth's sediment record pointed to an era when interstellar material had access to Earth's surface in a way that is not happening today. The combination of iron-60 and plutonium-244 in the same ancient rock layers, at concentrations above background levels from a globally consistent time period, pointed toward a moment when Earth sat in open interstellar space. The model and the physical evidence aligned. Scientists stopped treating the compressed heliosphere scenario as a theoretical exercise. It had happened. The solar system had crossed through something dense enough to crush the heliosphere inside Earth's orbit, and Earth had survived it. But survival and consequence are two different things. Because during that same time period, 2 to 3 million years ago, something else was happening on Earth. 2 to 3 million years ago, Earth was a different place. The planet had continents in roughly the same positions they hold today. The oceans were present. Life was well established. Early human ancestors were walking upright across the grasslands of Africa. The world looked familiar enough that you would recognize it from a distance, and yet the sky above it was different in ways no human alive today has ever experienced. With the heliosphere compressed inside Earth's orbit, the planet sat exposed to the interstellar medium. The solar wind still blew from the sun, still created aurora, still shaped Earth's magnetosphere. But the outer layers of the heliosphere, the termination shock, the heliosheath, the heliopause, were all pulled back close to the sunday. The first line of defense against interstellar material was gone. What replaced it was open space. The cold, thin gas between the stars pressed directly against the edge of Earth's magnetosphere. Interstellar, neutral hydrogen, traveling at tens of miles per second, flowed through the inner solar system unimpeded. Iron-60 from distant supernova explosions arrived at Earth's surface instead of being blocked at the heliosphere's outer wall. Galactic cosmic rays flooded in at a higher rate. These are high-energy particles, protons, helium nuclei, heavier atomic nuclei, moving at close to the speed of light. The heliosphere normally scatters and absorbs a significant fraction of them before they reach the inner solar system. With the heliosphere compressed near the Sun, the cosmic ray intensity at Earth's distance from the Sun increased. Earth's magnetic field and atmosphere still provided protection. The magnetosphere deflected charged particles above a certain energy threshold. The atmosphere absorbed and fragmented particles that made it through the magnetosphere. Life at the surface was never fully exposed to raw interstellar radiation, but the upper atmosphere absorbed more. Cosmic rays entering the atmosphere collide with nitrogen and oxygen molecules and produce secondary particles that cascade downward. At higher cosmic ray flux, more of these cascades reached lower altitudes. More ionization happened in the middle and lower atmosphere. What does that mean for climate? That question is still being worked through carefully. Ionization in the atmosphere affects the formation of aerosol particles. Aerosols influence cloud formation. Cloud coverage affects how much sunlight the planet reflects back into space. More clouds at certain altitudes cool the surface. Fewer clouds warm it. Scientists who have modeled this chain of effects find that the direction of influence, more cosmic rays, more atmospheric ionization, more low-altitude clouds, more cooling, is physically plausible. The size of the effect is debated, but the direction is consistent with what the geological record shows for that time period. Because 2 to 3 million years ago, Earth was entering a prolonged period of climate cooling. Ice sheets were expanding in the northern hemisphere. The global climate was shifting toward the Ice Age cycles that would dominate the next 2 million years of Earth's history. The interstellar cloud encounter and the onset of glaciation happened at the same time. Scientists are careful to point out that other factors also drove the ice ages, including changes in Earth's orbit and shifts in ocean circulation. The interstellar crossing was probably one factor among several, but the timing is striking. The chemical fingerprints are in the rock. The model matches the evidence. And the question of what caused Earth's Ice Age era may have an answer that starts 11 billion miles above the clouds. The Ice Ages are one of the great puzzles of Earth's climate history. For most of the planet's 4.5 billion year life, Earth was warmer than it is today. There were brief icy periods scattered through deep time, but for long stretches, the planet had no permanent polar ice caps at all. Dinosaurs lived in what are now Arctic region. Forests grew near the South Pole. The cold, cyclical glaciations that carved out the Great Lakes and buried much of North America under miles of ice were an unusual condition, not the norm. Then, roughly 2 to 3 million years ago, the cycles began. Ice sheets grew and shrank on roughly 100,000-year timescales. The glaciations deepened. The cooling trend persisted. Earth entered the pattern of ice ages that modern humans evolved within. Scientists have identified several contributing factors. Changes in Earth's orbital tilt and the shape of its orbit around the Sun, known as Milankovitch cycles, affect how much solar energy hits different latitudes at different times of year. Shifts in the position of the continents affect ocean currents. The rise of the Himalayas changed atmospheric circulation. Decreasing carbon dioxide in the atmosphere over geological time allowed more heat to escape into space. All of these factors are real. All of them contributed. The ice ages had many causes stacking on top of each other over millions of years, but none of those explanations fully accounts for the specific timing of when the deep glaciation cycles began. Orbital cycles were present before 2 to 3 million years ago. Continental positions shifted gradually. Carbon dioxide declined over much longer timescales. The sharpest transition in Earth's climate record, the moment when ice sheet formation accelerated dramatically and the deep glacial cycles locked in, falls right in the range of the interstellar cloud encounter. Researchers who published the heliosphere compression model in 2024 were direct about this. They pointed to the timing of the interstellar cold cloud encounter as a potential trigger or amplifier of the glaciation onset. A compressed heliosphere, allowing higher cosmic ray flux, could have pushed a climate system already near a threshold into full glaciation. The word trigger is used carefully in science. A trigger does not mean the only cause. It means the factor that pushed a system already under stress over the edge. A match does not cause a forest to burn unless the forest is dry. The orbital cycles and continental changes may have been drying out Earth's climate, setting it up for glaciation. The interstellar cloud encounter may have lit the match. This idea is compelling but unproven. The cosmic ray climate connection depends on physical chains with several links, and each link has uncertainties. Critics of the idea point out that the correlation in timing could be coincidence. Multiple factors converged around the same period for independent reasons. What the 2024 study did was demonstrate that the heliosphere compression is physically possible, and that the timing matches the geological evidence better than scientists previously recognized. The Ice Age question remains open, but the solar system's journey through interstellar space just became a serious candidate for a piece of the answer. And if it happened before, it could happen again. Suppose the solar system, right now, began moving into a region significantly denser than the local fluff. The heliosphere would not collapse instantly. The solar system moves at roughly 52,000 miles per hour relative to the surrounding interstellar gas. A cloud dense enough to substantially compress the heliosphere would have to be encountered at that speed, and the transition from the cloud's edge to its denser interior would take years to decades to fully impact the heliosphere. Scientists model this as a gradual process. The heliopause begins to move inward. The termination shock follows, retreating toward the sun over decades and centuries. The heliosheath thins. The compressed magnetic zone at the outer boundary intensifies. For the first few centuries of a moderate encounter, changes at Earth would be subtle. The cosmic ray flux reaching the inner solar system would increase, but slowly. Earth's atmosphere and magnetosphere would absorb the additional particles at roughly the same rate they absorb them today, just with a higher incoming load. Over centuries to millennia, if the compression continued, the heliosphere would reach a new equilibrium at a smaller size. How small depends entirely on how dense the cloud is. A cloud twice the density of the local fluff might reduce the heliosphere's radius by a modest amount. A cloud 10 times denser would compress it far more. A cloud hundreds of times denser, the extreme case modeled for the ancient encounter, would collapse it nearly to the sunday. For a moderate compression, the effects on Earth would be mostly subtle. higher cosmic ray flux reaching the upper atmosphere, slight changes in atmospheric ionization, possible effects on cloud formation chemistry. Scientists would measure the change with instruments long before it caused any direct biological effect. For a significant compression, the radiation environment of the inner solar system would shift meaningfully. More energetic particles would penetrate deeper into the atmosphere. The long-term climate effects could become substantial. The chemistry of the upper atmosphere, including ozone, could change. For the extreme case, the scenario explored in the ancient encounter model, Earth would face the interstellar medium directly. The planet's magnetosphere would be the only remaining shield. It is a good shield for charged particles, but does not stop neutral interstellar gas from flowing through the inner solar system. Interstellar hydrogen and heavier atoms would reach Earth's upper atmosphere in quantities that are essentially zero today. The specific density of the G-cloud, at the exact location the Sun will enter, it is unknown. Scientists have average estimates for the G-cloud's properties. The actual material at the crossing point could be near the average, significantly above it or significantly below it. This is the honest picture. Scientists know the type of event that could happen. They have physical evidence that a severe version happened before, and they do not yet have the observational tools to predict how severe the next crossing will be. The data that would answer that question is arriving slowly from the outer edges of the solar system, even now. Galactic cosmic rays are everywhere. They come from every direction. They were produced by supernova explosions, by pulsar winds, by the shock fronts of colliding galaxies, by violent processes scattered across hundreds of thousands of light-years of the Milky Way. They travel at close to the speed of light. A single high-energy cosmic ray proton carries as much energy as a baseball thrown at a moderate speed, compressed into a particle smaller than an atom. Earth gets hit by roughly 1 cosmic ray per square inch of ground per minute at sea level. Most of them have already been shattered and scattered by the time they reach the ground, after colliding with nitrogen and oxygen molecules high in the atmosphere and producing cascades of secondary particles. The raw particles from space almost never reach the surface. What arrives at ground level is the debris of collisions that happened miles above. The heliosphere shapes how many of these particles reach Earth in the first place. Scientists measure the cosmic ray flux at the edge of the solar system using spacecraft. Voyager 1, after crossing the heliopause, measured the full unshielded galactic cosmic ray intensity. Inside the heliosphere, the flux is lower because the solar wind's magnetic field scatters and absorbs a fraction of the incoming particles before they reach the inner planets. The exact reduction depends on the particle's energy. Very high-energy cosmic rays barrel straight through the heliosphere as if it were barely there. Lower-energy particles are deflected more effectively. The heliosphere is most useful as a shield against the moderate-energy particles, the ones that would otherwise reach Earth's atmosphere in larger numbers and cause more ionization at lower altitudes. When the heliosphere compresses, the path through it gets shorter. Moderate energy particles that the heliosphere would normally scatter multiple times before they reach Earth's orbit get through in fewer scattering events. More of them arrive at Earth's upper atmosphere, still carrying most of their original energy. The consequences cascade through the atmosphere in layers. The top of the atmosphere sees the increase first. High-altitude ionization rises. Aerosol chemistry changes. Cloud formation at high altitudes shifts. Lower in the atmosphere, the changes are smaller but still present. Earth has a natural record of past cosmic ray intensity. Cosmic rays hitting the atmosphere produce beryllium-10, a rare isotope that falls to Earth's surface and gets buried in ice cores and sediment. Higher cosmic ray flux produces more beryllium-10. Scientists drill into Antarctic ice cores and Greenland ice cores, measure the beryllium-10 concentration layer by layer, and reconstruct the history of cosmic ray intensity over hundreds of thousands of years. Those records show fluctuations. The cosmic ray flux at Earth has not been constant. It shifts with the Sun's activity cycle on short timescales. It may shift on longer timescales with the heliosphere's size. Pinning the longer-term shifts to specific causes requires connecting multiple lines of evidence: ice cores, sediment samples, heliosphere models, galactic magnetic field measurements. Scientists are building that case carefully, knowing the connection is real in principle, even where the specific magnitudes remain uncertain. The ancient encounter left iron-60 in ocean sediment. Future encounters may leave their own marks. Here is a question that sounds simple and turns out to be surprisingly hard to answer. Where exactly is the sun inside the local fluff right now? Scientists have been debating this for decades. The disagreement is not about whether the local fluff exists that is well established. The disagreement is about the sun's precise position within it, and specifically how close the sun is to the cloud's edge in the direction it is moving. Some studies place the sun near the center of the cloud, others place it close to one edge. The most recent and detailed models suggest the sun sits in the forward half of the cloud relative to its direction of travel, meaning it is closer to the leading edge than the trailing edge. A team that published one of the most comprehensive maps of the local fluff estimated the sun may be within a few tenths of a light year of the cloud boundary in the direction it is heading. A few tenths of a light year is roughly 2 to 3 trillion miles. The solar system is covering that distance at its current speed in somewhere between 40,000 and 100,000 years. But other teams analyzing the same data reach different conclusions. Some measurements of the interstellar hydrogen flowing into the solar system suggest properties more consistent with the cloud's interior. Other measurements hint at a transition zone. The root of the disagreement is the measurement method. Scientists are building a three-dimensional map using absorption measurements along dozens of lines of sight. Each line of sight passes through a slightly different part of the cloud. Where the lines of sight are dense, the map is detailed. Where they are sparse, the map has gaps that get filled with model assumptions. The sun's position in the cloud is inferred from where the local fluff's properties best match what the solar system is sampling from the inside. And those inside measurements, the flow of neutral atoms into the solar system, the magnetic field direction at the heliosphere's edge, the properties of the ribbon discovered by the Interstellar Boundary Explorer, tell a story that scientists are still interpreting. One astronomer summarized the situation plainly in a review paper. The sun is probably close to the edge of the local fluff. Exactly how close depends on which measurements you weight most heavily. The range of reasonable estimates spans from already in the transition zone to still a few thousand years away from the boundary. That range has enormous practical implications. If the sun is already in the transition zone, the heliosphere is already responding to the G-cloud's influence. The changes are already beginning, slowly and subtly. If the sun still has a few thousand years inside the local fluff, the heliosphere is still in a stable period. Current observations cannot definitively settle the question with the instruments available today. Future missions designed to measure interstellar properties from multiple directions simultaneously could narrow the uncertainty significantly. Until then, the sun's exact position in the cloud is genuinely unknown, a scientific mystery, measurable in trillions of miles, that nobody has yet solved with certainty. Every diagram of the local fluff shows it as a defined shape with visible boundaries, a cloud with edges you could trace with a pencil. That is a useful simplification. The reality is far messier. Interstellar gas clouds form from the turbulent dynamics of the galaxy. Gas gets compressed by supernova shockwaves. Gravity pulls it together in some places. Stellar radiation blows it apart in others. The result is structures with extremely uneven density profiles. A cloud has a core where gas is denser, flanks where it thins out, filaments stretching away in directions shaped by the local magnetic field, and ragged edges where the cloud's material bleeds into the surrounding medium. The local fluff's edge, in the direction the solar system is heading, is one of the least well-defined parts of its boundary. On one side, the local fluff merges into the G-cloud. On another side, it merges into a different neighboring structure. On other sides, it borders the hot, thin gas that fills most of the local bubble. Each of those interfaces has its own character. The border between the local fluff and the hot local bubble gas is probably relatively sharp because the two materials are so different in temperature and density that they do not mix easily. Hot gas and cold gas tend to stay separated, but the interface between the local fluff and the G-cloud is between two structures that are more similar to each other in temperature and composition. They mix more easily. Their shared boundary is thicker and more gradual. The magnetic field adds another layer of complexity. Magnetic field lines thread through the cloud and connect to the wider galactic field. Where field lines cross the cloud's boundary, they create channels that the gas preferentially follows. Dense threads of material can extend far beyond the cloud's main body along these field lines, like fingers reaching outward. Scientists studying the local fluff have found evidence of such structures. Narrow tubes of denser gas, aligned with the magnetic field, extending toward the solar system's path. Whether any of those tubes sit directly in the solar system's trajectory is unknown. This is what makes the cloud's boundary story more complex than a simple, "we are leaving one cloud and entering another." The real boundary is a multi-layered, magnetically structured, irregularly shaped transition zone that could contain patches of dramatically different density scattered throughout an otherwise gradual gradient. A ship crossing from the Atlantic into the Caribbean does not experience a single moment of transition. The water gets warmer, the color shifts, the currents change, but at no single GPS coordinate does the ocean flip from one to the other. The solar system's crossing into the G-cloud region is similar, an extended, complex transition with no single defining moment. What scientists can say is that the solar system is somewhere in that transition, heading deeper into it, and the farther it goes, the different the heliosphere becomes. The next discovery showed that the G-cloud itself was doing something to space in the direction the solar system is heading, something that a 2025 study could not fully explain. The interstellar magnetic field is one of the most important and least visible forces shaping the solar system's environment. Magnetic fields thread through the entire galaxy. They run through clouds, through the space between clouds, through the hot gas of supernova remnants, and through the thin plasma filling the galactic disk. They connect structures across light years. They guide the motion of charged particles. They shape the way gas clouds move and compress over thousands of years. The local fluff has its own magnetic field threading through it. Measurements of how polarized light from background stars rotates as it passes through the cloud reveal the field's general direction. The local fluff's field points in a direction scientists can measure and describe as a vector in three-dimensional space. The G-cloud has a different field direction. This matters because of what the magnetic field does to the heliosphere. The outside field presses against the heliosphere from all sides, but it does not press equally. The direction of the field relative to the solar system's motion determines how the heliosphere distorts. It is the external field's orientation that produces the comet tail shape and the tilted heliotail that ibex map. The G-cloud's field, pointing from a different direction than the local fluff's field, would apply pressure at different angles to the heliosphere. The bubble would not simply get smaller as the solar system enters the G-cloud. It would also reshape itself. The nose would reorient. The tail would swing. The bright ribbon that ibex discovered would arc across a different part of the sky. Researchers published models predicting the heliosphere's new shape inside the G-cloud's magnetic environment. The changes were substantial. The compressed leading face of the heliosphere would shift by tens of degrees from its current orientation. Regions of the heliosphere that currently face the incoming interstellar flow obliquely would face it more directly. The directional change matters for cosmic ray shielding because the heliosphere does not block all directions equally. The compressed nose region, with its piled-up magnetic field, blocks incoming particles more effectively than the flanks or the tail. If the nose rotates relative to the direction of incoming galactic cosmic rays, the shielding in specific directions changes. One finding that came out of these models was particularly striking. The G-cloud's magnetic field appears to point in a direction that would cause the heliosphere's compressed leading face to shift substantially from its current orientation. The heliosphere would reorganize around the new pressure geometry within thousands of years of entering the G-cloud. This is a real, predictable physical consequence that follows directly from the measured properties of the two clouds. The local fluff field direction is measured. The G-cloud field direction is measured. The resulting heliosphere geometries in each environment are calculated from physical laws that scientists are confident in. The uncertainty is not in the physics. The uncertainty is in the exact density, the exact field strength, and the exact location where the solar system will first feel the G-cloud's magnetic influence. That location may be closer than any measurement had suggested, and a separate discovery from the farthest end of the measurement scale confirmed that the solar system's motion through the universe was stranger than standard models assumed. In November of 2025, a team of researchers published a paper that sent a ripple through cosmology. They had been analyzing data from a radio telescope network called the Low Frequency Array, a system of thousands of individual antennas spread across Europe, collectively acting as a single enormous telescope. Their target was distant radio galaxies hundreds of millions of light years away, scattered across the entire sky. The specific thing they were measuring was a pattern called the radio dipole. Here is what a dipole means in this context. When you move through space, the things ahead of you appear slightly blue shifted, and the things behind you appear slightly red shifted. This is a straightforward effect of motion. The movement also makes the sky slightly brighter and denser in the direction you are moving toward. This asymmetry is called a dipole, a difference between two opposite directions. Earth is not sitting still. It orbits the Sunday. The Sun orbits the galaxy. The galaxy moves within its local group of galaxies, and the entire local group moves through the universe relative to the cosmic microwave background, the ancient light left over from the early universe. Scientists have known for decades that the solar system moves relative to the cosmic microwave background at roughly 370 miles per second. That motion was measured precisely and agreed across many observations. The radio dipole from distant galaxies should, in principle, line up with that motion. If you are moving at a known speed in a known direction, both the ancient microwave light and the distribution of distant radio galaxies should show dipoles pointing in the same direction and with a matching size. The 2025 study found that they do not match. The radio galaxy dipole was 3.7 times stronger than the motion measured from the cosmic microwave background would predict. The direction was similar, but the size of the asymmetry was dramatically larger, 3.7 times. That is a massive discrepancy. It is far beyond any measurement error that calibration issues could explain. This result, if it holds up under further scrutiny, means one of several things. Either the solar system is moving significantly faster relative to the large-scale structure of the universe than the microwave background measurement suggests, or there is something asymmetric about the distribution of radio galaxies in the local universe that creates a fake dipole signal, or the standard model of cosmology is missing something important about how large-scale structure forms. Scientists immediately debated all three possibilities. The study was peer-reviewed and published in a top journal, but the scientific community does not accept a single study as settled proof of something this significant. Independent verification using other radio surveys was called for. This discovery is real, and it is unresolved. And it is a completely separate story from the local fluff and the G-cloud. Understanding why they are separate is essential to understanding both. Understanding the radio dipole result requires stepping back to the scale of the entire observable universe. The universe, as best scientists can tell, is roughly the same in all directions on the largest scales. Spread billions of light years in every direction, galaxies are distributed roughly uniformly. No single direction has dramatically more galaxies than the opposite direction. This uniformity on large scales is one of the foundations of the standard model of cosmology. But uniformity does not mean perfect smoothness. On smaller scales, hundreds of millions of light years, there are structures, galaxy clusters, filaments, voids. The universe has a web-like texture at those scales. Some regions are denser than others. When the solar system moves through space, that motion creates the dipole pattern described in the previous chapter. But here is a subtlety that makes the radio galaxy measurement tricky. The radio galaxies being counted are not uniformly distributed in distance. Some are closer, some are farther. If the nearby universe happens to have more radio galaxies in one direction than the other for reasons unrelated to our motion, a local overdensity or a local void, that imbalance would add to or subtract from the motion dipole, its signal. Scientists call this a source count dipole contribution from large-scale structure. It is a potential contaminant in the measurement. The 2025 study tried to account for this carefully. The researchers used a very large sample of radio galaxies and applied statistical methods designed to separate the motion dipole from the structure contribution. Their conclusion was that even after accounting for local structure, the remaining dipole was still much larger than the microwave background motion predicts. But other scientists have challenged whether the structure contribution was fully removed. The debate centers on how well the statistical corrections work when the galaxy sample has observational biases. Some directions of the sky are harder to survey than others because of our own Milky Way galaxy sitting in the way. This is the current state of the science. A striking measurement, a physical explanation that would require revising cosmology if it holds up, and active debate about whether the measurement is fully clean. The reason this matters for the solar system's journey into unmapped space is indirect but real. If the solar system's true motion through the universe is significantly different from what the microwave background suggests, then the models scientists use to predict the solar system's path through the interstellar neighborhood, including its trajectory toward the G-cloud, may need adjustment. The speed and direction the solar system is moving determine which interstellar clouds it will encounter and when. A different speed changes the timeline. It changes which patch of the G-cloud the Sun enters. It could change whether the encounter is mild or severe. The 2025 result has not been confirmed yet. If it is eventually verified, it would feed into the local fluff and G-cloud story in exactly that way. For now, it hangs as a genuine open question at the edge of what cosmology can explain. At this point in the story, two separate discoveries sit on the table. One is about the solar system drifting toward the edge of the local fluff and approaching the G-cloud. That story happens in the immediate galactic neighborhood, within a few dozen light years of the Sunday. It involves the heliosphere, interstellar clouds, galactic cosmic rays, and the shielding of the inner solar system. Its timescale is thousands of years. The other is about the radio galaxy dipole from the 2025 study, suggesting the solar system may be moving faster relative to the large-scale structure of the universe than standard cosmology predicts. That story happens at the scale of hundreds of millions to billions of light years. It involves the motion of the entire galaxy relative to the cosmic web. Its implications, if confirmed, would touch the foundations of cosmology. Both involve the solar system moving through space, and that shared theme has led some people to blend them into one story. They are not the same story. The clouds near the solar system, the local fluff, the G-cloud, the local bubble, exist at scales of a few to a few hundred light years. The radio galaxy dipole involves structures at scales of millions and billions of light years. These are so different in scale that they are essentially disconnected physical questions. The motion that creates the radio galaxy dipole is the motion of the entire Milky Way galaxy relative to the large-scale distribution of matter in the universe. That galaxy-scale motion is hundreds of times faster than the solar system's motion through the local fluff. The interstellar cloud story is entirely contained within the Milky Way. The radio dipole story involves the Milky Way's position in a much larger cosmic structure. Confusing them would be like saying a person walking across a continent is experiencing the same journey as the continent drifting on tectonic plates. Both involve motion. The scale difference makes them completely separate phenomena. Scientists who study the local fluff and heliosphere do not need the radio dipole result to justify their work. The cloud boundary story stands on its own evidence: stellar absorption measurements, heliosphere models, Voyager data, IBEX observations, and the geological record in deep-sea sediment. All of that evidence is independent of whatever the radio galaxy dipole means, and the radio dipole researchers are not claiming anything about the G-cloud or the heliosphere. Their measurement concerns the distribution of very distant galaxies across the sky. The two stories both point to genuinely interesting and unresolved questions about the solar system's place in the universe. They amplify each other in terms of how strange and unfinished the picture of our cosmic position turns out to be, but treating them as one claim would misrepresent both. The solar system is moving toward unmapped local space. The solar system may also be moving faster through the large-scale universe than expected. Both are real open questions, and both belong to different chapters of a very large story. Nobody has flown a spacecraft to the G-cloud boundary and taken a sample. The farthest human-made objects in space are Voyager 1 and Voyager 2. Voyager 1 has traveled over 14 billion miles from the Sun since its launch in 1977. It crossed the heliopause over a decade ago and is now sampling the true interstellar medium, but only at one point, in one direction. To map an entire three-dimensional cloud boundary from a single in-situ measurement is like trying to describe an ocean from one beach. So scientists use every indirect tool available. It is a form of detective work done across trillions of miles, using signals that pass through or originate at the boundary and then travel to instruments near Earth. Neutral atoms are one of the most useful messengers. Unlike charged particles, neutral atoms are not deflected by magnetic fields. They travel in straight lines from wherever they were produced or entered the solar system. The heliosphere is permeable to them. Neutral hydrogen, helium, oxygen, and other atoms from the interstellar medium drift inward through the heliosphere and can be detected by instruments in Earth orbit or on spacecraft in the inner solar system. The Interstellar Boundary Explorer measured the flow of these neutral atoms precisely, the direction the atoms come from, their speed, and their temperature all encode information about the interstellar cloud just outside the heliosphere. When the measurements matched the local fluff model, that confirmed the Sun is still inside the local fluff. When small discrepancies appeared in the neutral hydrogen flow direction, they suggested the boundary is closer than the simple model predicts. Energetic neutral atoms are a related tool. These atoms form at the edge of the heliosphere when a solar wind proton captures an electron from an interstellar neutral and becomes uncharged. The newly neutral atom then flies inward in a straight line. Mapping their arrival directions from Earth orbit produces a picture of the entire heliosphere boundary, which is exactly what the Interstellar Boundary Explorer used to find the ribbon. Magnetic field measurements from Voyager 1 and 2 give a direct reading of the interstellar magnetic field just outside the heliopause. Those readings are compared to models of the local fluff and G-cloud field directions to determine which environment the solar system is sampling. Cosmic ray intensity at the heliopause gives information about the galactic particle environment. Changes in that intensity over time would signal a changing interstellar environment, and starlight absorption measurements continue to improve. Each new high-resolution stellar spectrum from a star at the right distance and direction adds another data point to the cloud map. The three-dimensional picture of the interstellar neighborhood keeps getting refined. Together, all of these tools give scientists an indirect but increasingly detailed sense of the interstellar weather just beyond the solar system's edge. The boundary has not been physically reached by any spacecraft that can return data in real time, but it is being watched from many angles simultaneously, and the picture those angles are assembling suggests the next layer of interstellar space. The solar system is entering is doing something no single instrument has fully characterized. The G-cloud is not the end of the story. Step back far enough, and the whole neighborhood the solar system moves through comes into view. The local fluff and the G cloud are both tiny features inside a much larger structure called the local bubble. The local bubble is a cavity in the interstellar medium. It stretches roughly 1,000 light-years across in some directions. Though its shape is irregular, inside the bubble, the density of interstellar gas is far lower than in the denser clouds and filaments outside it. The gas inside the bubble is hot millions of degrees and extremely thin. The Sun, the local fluff, the G cloud, and dozens of other small cloud structures all float inside this enormous hollow region. The local bubble was carved out by a series of supernova explosions roughly 10 to 20 million years ago. A group of massive stars in the neighborhood of the current solar system lived fast and died violently. When stars of that mass explode as supernovae, they blast outward a wave of hot, fast-moving gas that sweeps away the surrounding interstellar medium. Enough supernovae in the same region over millions of years scooped out a vast cavity in the galaxy's gas disk. The walls of the local bubble are where the swept-up gas accumulated. Dense shells of compressed interstellar material ring the bubble at distances of hundreds of light-years. These walls glow in soft X-rays and contain some of the densest molecular clouds in the solar neighborhood. The Sun will orbit the center of the Milky Way roughly once every 230 million years. Over that long orbit, the Sun passes through many different environments in the galaxy. It crosses spiral arms, moves through diffuse regions between arms, passes near dense molecular clouds, and travels through regions where supernova activity is high or low. The solar system entered the local bubble sometime in the last few million years. Before entering the bubble, the solar system was moving through denser interstellar gas. The transition into the bubble's hot, thin interior represented a period of reduced outside pressure on the heliosphere, a relatively sheltered phase compared to what came before. The local fluff and G cloud are small, dense patches inside this otherwise thin bubble. They are remnants material that survived the supernova explosions that created the bubble or condensed later from cooling gas. Their presence inside the bubble gives the Sun's immediate neighborhood a local complexity that the bubble's average properties do not capture. Eventually, over millions of years, the solar system will leave the local bubble. It will encounter the bubble's walls, those dense, compressed shells of gas where the old supernova shockwaves piled up the surrounding material. Those walls are far denser than anything the solar system is approaching now. Crossing into a bubble wall would compress the heliosphere dramatically, more dramatically than the ancient cloud encounter 2 to 3 million years ago. The timescale for such an encounter is millions of years in the future, far beyond any human timeframe. But the principle is the same as everything discussed in this story. The heliosphere is not permanent. The environment changes, and the consequences of those changes reach inward to where life exists. Here is the part of the story that should actually reassure you. The solar system is roughly 4.5 billion years old. In that time, it has orbited the galaxy nearly 20 times. Each orbit takes the solar system through different regions of the Milky Way, different interstellar gas densities, different magnetic field environments, different levels of cosmic ray flux. During those 20 orbits, the solar system has crossed through interstellar clouds many times. Some of those crossings were probably mild. The heliosphere compressed slightly, the cosmic ray flux at Earth increased modestly, and life continued without interruption. Some crossings were probably more severe. The 2 to 3 million year ago encounter, modeled in the 2024 study, involved a cold, dense cloud that may have compressed the heliosphere inside Earth's orbit. Life on Earth was well established at that point. Early human ancestors were walking and using tools. Complex ecosystems existed on every continent. Ocean life was diverse and abundant. The interstellar cloud crossing did not end life on Earth. The planet's atmosphere is a remarkably effective shield against the direct effects of interstellar gas. Even with the heliosphere compressed, Earth's own magnetic field deflected most charged particles. The atmosphere absorbed and fragmented high-energy radiation. The interstellar medium that reached the surface was too thin to cause direct biological harm to organisms living below the protective air layer. What the crossing may have influenced was climate. The ice age cycles that followed the ancient encounter imposed enormous stress on ecosystems. Species went extinct, habitats changed. The grasslands of Africa that human ancestors evolved in spread as forests retreated under the cooling climate. But life adapted. The very evolutionary pressures imposed by the changing climate may have been part of what drove the development of the large, flexible brains that define the human lineage. The stress of a changing world, caused in part by a changing heliosphere, may have accelerated the evolutionary trajectory that eventually led to the species asking these questions. The ancient crossing did not destroy life. It changed the conditions under which life evolved. That is a different and arguably more interesting story. Over 4.5 billion years of cloud crossings, the continuity of life on Earth has never been broken. The heliosphere has compressed and expanded. The cosmic ray flux has risen and fallen. Climates have shifted, and life has persisted through all of it, adapting, diversifying, and eventually developing the intelligence to look back at the clouds it has already crossed. The next crossing will impose its own conditions. If the solar system enters a denser region of the G-cloud, the heliosphere will adjust. The radiation environment will shift. Climate may respond over long timescales. Life will face new pressures, and life will almost certainly adapt to those too. 10,000 years is a long time for a human mind to picture. Every civilization that has ever existed falls within the last 10,000 years. The oldest written records are younger than that. The pyramids of Egypt are younger than that. And yet 10,000 years is roughly the timescale scientists attach to when the solar system may fully leave the local fluff or may already be leaving it. On that timescale, the heliosphere will begin to respond to whatever the solar system encounters beyond the local fluff's edge. If the boundary region is thin and the G-cloud's near-edge properties are only slightly denser than the local fluff, the changes will be gradual and subtle over the entire 10,000-year period. If the solar system is already in the transition zone, a real possibility that current measurements cannot rule out, then the changes are already beginning. The heliosphere is already starting to reorganize around a slightly different external pressure and magnetic geometry. The ribbon that Ibex mapped may be starting a slow shift, too gradual to measure within a human lifetime but real on century timescales. Scientists modeling the heliosphere's expected behavior over the next several thousand years find a consistent picture, regardless of the exact density of the G-cloud at the crossing point. The heliopause will move. The shape of the heliosphere will change. The outer boundary will reorganize around the new magnetic geometry of the region the Sun enters. In the mild scenario, this is an adjustment humans would never detect without instruments. The cosmic ray flux at Earth might increase by a few percent. The upper atmosphere would absorb slightly more ionizing radiation. Climate effects, if any, would be at the boundary of detectability against the background noise of natural climate variability. In a more significant scenario, the heliosphere's compression could be large enough to produce a measurable increase in cosmic rays at Earth within centuries. Climate researchers would potentially see the signal in high-altitude cloud formation data or in ice core records centuries from now. In the most dramatic scenario, if the solar system encounters a dense knot of gas at the cloud boundary, the compression could be rapid and severe. Scientists cannot predict this because the cloud maps do not have fine enough resolution to reveal such knots. They could be there. They could also not be there. Human civilization, existing 10,000 years from now, if it does exist, would likely have instruments sensitive enough to detect and monitor whatever changes the heliosphere is going through. The boundary crossing would be observable in real time by that civilization, with satellite arrays, deep space probes, and measurement systems far more capable than anything built today. The scientists of that future would not be surprised. The work being done now is giving them the foundation of understanding they will need. Every measurement taken today, every model refined this decade, Every paper published about the local fluff and G-cloud is a brick in the foundation of knowledge that will eventually allow those future observers to watch the crossing unfold. The story that started with an ancient cloud encounter and iron 60 in ocean sediment will continue being written. The next chapters will be written by people who have not been born yet. Earth has 2 layers of protection against the radiation of space. The first layer is Earth's own magnetosphere. Generated by the churning of liquid iron in the planet's outer core, Earth's magnetic field wraps around the entire planet in a teardrop shape. The field deflects most charged particles arriving from the sun and from deeper space. Without it, the solar wind would strip away the upper atmosphere over millions of years, the same way Mars lost most of its atmosphere after its own magnetic field weakened billions of years ago. The magnetosphere is Earth's personal shield. It handles the local threat from the sunday. The heliosphere is the second layer. It handles the threat from everywhere else, the galaxy, the cosmic ray environment, the interstellar medium. It operates on a scale billions of times larger than the magnetosphere. But it follows the same basic principle. Create a boundary where the threat level drops. The heliosphere weakens under 2 conditions. The first is a weakening sunday. If the solar wind output drops significantly, less pressure pushes outward and the heliosphere contracts. The sun goes through an activity cycle every 11 years, where its wind output varies slightly, and scientists have also identified longer period cycles where solar activity may drop to very low levels for decades at a time. During those quiet periods, the heliosphere does shrink modestly, and cosmic ray flux at Earth shows a corresponding increase. The second condition is increased outside pressure. A denser interstellar cloud pressing against the heliosphere from outside pushes the boundary inward, regardless of what the sun is doing. This is the condition the solar system is approaching. Both conditions can happen simultaneously. If the solar system enters a denser cloud during a period of reduced solar activity, both sides of the pressure balance shift at the same time. The heliosphere faces maximum compression. The outer wall retreats most aggressively toward the sunday. Scientists have looked at Earth's climate record for signs of periods when both factors aligned. The data are suggestive in places, but not conclusive. The signal of heliosphere-driven cosmic ray change is small enough that it overlaps with other climate drivers, making it genuinely difficult to isolate. But the physics is clear. The heliosphere is a dynamic structure. Its size and shape respond to conditions both inside and outside the solar system, and the conditions outside are changing. There is one more thing the heliosphere does that goes beyond radiation shielding. It filters what can physically enter the inner solar system. Interstellar dust grains, tiny particles produced in dying stars and scattered through the galaxy, are deflected by the heliosphere's magnetic field. Larger, electrically neutral particles can drift through, but the charged fraction of interstellar dust gets sorted by the magnetic boundary. As the heliosphere changes geometry and possibly shrinks, the filtering of interstellar dust changes too. Different sizes and types of particles gain or lose access to the inner solar system. Some of those particles contribute to atmospheric aerosols. Their input into the upper atmosphere affects atmospheric chemistry at levels scientists are still measuring. The heliosphere is not just a passive boundary, it is an active filter, and its properties as a filter are about to change. Here is where the story stands right now. The solar system is moving. It has always been moving. But right now, for the first time in human history, scientists have enough measurements to understand with real detail what that motion means and what lies in the direction the sun is heading. The local fluff is real. The solar system has been inside it for tens of thousands of years. Its edge is close, possibly within the next few thousand years of travel, possibly already being crossed in the current transition zone. The measurements are not precise enough to say for certain where the sun sits within the cloud boundary. The G-cloud is real. It lies beyond the local fluff. Its magnetic field points in a different direction. Its density is somewhat higher than the local fluff's density, though how much higher at the specific entry point the solar system will encounter remains unknown. The heliosphere will reorganize its shape as the solar system enters the G-cloud's magnetic environment. The evidence of past cloud crossings is real. The Iron-60 and plutonium-244 in deep-sea sediment layers are physical facts. The timing of their elevated deposition matches the time frame of a modeled cloud encounter 2 to 3 million years ago. The heliosphere compression that would allow interstellar material to reach Earth's surface is physically possible and has been modeled carefully. The connection between that ancient crossing and the onset of Earth's ice age cycles is plausible and supported by timing, but not proven as a direct cause. Multiple factors drove the ice ages. The interstellar cloud encounter may have been one of them. The 2025 radio galaxy dipole result is real and unresolved. It suggests the solar system's motion through the large-scale universe may be faster than the standard model predicts. That result does not change the local fluff and G-cloud story directly, but if confirmed, it would eventually feed into models of the solar system's long-term galactic trajectory. What scientists do not know is exactly where the transition zone boundary sits in the direction the solar system is heading. They do not know the G-cloud's precise density at the crossing point. They do not know whether dense knots of interstellar gas sit in the solar system's path. They do not know whether the heliosphere is already beginning to respond to the G-cloud's magnetic field. Every one of those unknowns is a scientific question being actively worked on. Every spacecraft dataset, every stellar spectrum, every heliosphere model update adds information. The picture has never been clearer than it is today, and it has never been more clear how much remains unmapped. The solar system is approaching a boundary. The heliosphere will change. Earth's radiation environment will shift over timescales that stretch from centuries to millennia. Life has crossed these boundaries before and continued. And somewhere out past 11 billion miles, in the direction the sun has been heading for millions of years, the galaxy is doing something no instrument has fully captured. The crossing has already begun.